So in this section, we're going to look at these aldol reactions followed by the dehydration to form the enone, and then subsequent steps that can be used. So let's look at an example here. Let's say we have butanal. So we have CH3, CH2, CH2, C double bond O, bond H, butanal. So a 4-carbon aldehyde or butanaldehyde. All right, we're going to use a relatively weak base, in this case, in the presence of ethanol. So what we're going to do is we're going to do the aldol reaction followed by the dehydration. So let's do exactly what we did before. What we're going to do is start by drawing the molecule with one hydrogen coming off of here, okay? Except for this time, what's going to happen is we're actually going to have 2 hydrogens come off of here if we have the dehydration occur after, because we're going to lose an H the first time to the base, and we're going to lose it the second time in the dehydration. So I'm going to redraw this with 2 hydrogens coming off. CH3, CH2, C, C double bond O, bond H. Now, this is going to be double bonded to this carbon. And this carbon, after the dehydration, is going to lose this OH. Before, we had 1 hydrogen lost here, and we got an OH over here. But then in the subsequent step, that second hydrogen is lost, and the OH is lost. That's where the water comes from. So now we're double bonded to this carbon. So essentially, we just changed this to a carbon. This is a H, and this is still a propyl group, if you will. Overall, it's 4 carbons, so it's a butyl group, but this is basically what we have. Okay, this gives us our conjugation. Double, I'll draw it in here, double, single, double bond, and this is after the dehydration occurs. Well, let's say that we then take this molecule and we add hydrogen and platinum. And you may remember from your alkene chemistry that this will hydrogenate this bond. So we could have CH3, CH2, C, now bonded to an H, bonded to a C, double bond O, bonded to an H. So this becomes a single bond. Now bonded to a C, bonded to an H, bonded to an H, bonded to a CH2, CH3, CH2, CH2. Okay, like that. So hydrogen and platinum can hydrogenate or add hydrogen to this double bond. Then we could, for example, use sodium borohydride. And you may recall that borohydride is a reducing agent, which causes this to become an alcohol. And what we end up with is CH3, CH2, CH, I'm just going to write that as CH, bonded to C, bond OH, bond H, bonded to C, H, I don't know why I wrote this as a C, this should be an H, bonded to an H, bonded to a CH3, CH2, CH2. So we started with a 4-carbon aldehyde, and we ended up with a 1, 2, 3, 4, 5, 6, 7, 8 carbon alcohol. So this can be a way to make larger molecules, as shown here. In the next one, let's look at a mixed aldol reaction followed by a dehydration. So in this case, let's say we start with 2 relatively simple aldehydes. So we have 2 simple aldehydes. They're not even ketones. So we have CH3, C double bond O, bond H, acetal. Okay, or acetaldehyde. Here we have this one, and we're going to add to it the same thing, except with 1 extra carbon. So propanaldehyde. Like so. Okay, now let's look at what products we could make. Well, it turns out we can make quite a large number of products. I'm just going to move this over so I have room to write all 4 of the products we could make. So let's look at first with this molecule, being the one that loses a proton. So here we're going to add some base, okay? Some relatively weak base in relatively small quantities. So let's look at this carbon being the alpha carbon and losing a proton. Now remember that we're going to also show the dehydration. So we want to show this with 2 carbons being lost. So it goes from CH3 to CH. C double bond O, bond H. Now, let's say it attacks itself. So it attacks this one. So now instead of double bond O, we essentially go to double bond C. That's this C, now double bonded. And this has a CH3 and an H. And again, we get our double, you can't see it there, single double bond. It's conjugated after the dehydration. So this is one possible product. Well, let's again look at this one, okay, this molecule. And let's say that it loses its alpha proton and then it attacks this one. All right, the opposite molecule, followed by a subsequent dehydration. So again, we want to draw this with 2 less hydrogens. So CH instead of CH3, C double bond O, bond H. But this time it attacks this one. So we get a double bonded to a C, bonded to an H, bonded to a CH3, CH2. Again, notice we've lost the C double bond O, and it essentially gets double bonded to the other molecule that lost its originally 1 proton from the alpha carbon, but ultimately it loses both because in the dehydration, we lose the second one. Let's look at the next example, okay? Let's say that this behaves as the alpha carbon and loses its proton. So I want to redraw this with no protons on this carbon. It's going to lose both after the dehydration. So we have CH3, C, C double bond O, bond H. Now, let's say it attacks itself. So this becomes double bonded to this carbon, which is attached to a hydrogen, which is attached to a CH3, CH2. Needless to say, to be able to draw all 4 of these things, you need some, practice. You got to practice drawing these things. All right, now last one. We lose this, and it attacks this one. So again, we draw this without its 2 hydrogens, CH3, C, C double bond O, bond H. Then it attacks this one. So essentially, we double bond where it was to an O, we double bond to this carbon. So we double bond it to a C, bonded to an H, bonded to a CH3, like so. So this gives us our molecules that we can use in order to have an aldol reaction or an aldol condensation reaction followed by a dehydration. We would get these 4 products. This is quite a mess. All right, we do not want a reaction where we get this complex mixture of products, and none of these are exactly the same. So they're all going to have slightly different physical properties, different melting points and boiling points, but they're going to be difficult to separate, and this is kind of a problem. So let's look at a way we might be able to fix this problem. Let's look at taking this molecule. Let me try again. All right, and we have a methyl group here, and 2 H's here, and 1 H here. And we're going to react it with this molecule, which is benzaldehyde, like so. All right, what are we going to get in the presence of, in this case, the weak base is NaOCH2, CH3. And I just need to point out again, this is not a weak base in the sense of bases like you learned in general chemistry. This is pretty strong. But compared to something like LDA, this is a weak base. And this would be done in ethanol as the solvent. So remember, the first reaction step of these reactions is to form the aldol, not the enone. So the aldol is formed by losing a hydrogen from the alpha carbon. So let's look at some examples here of where we could find a carbon with a hydrogen. So this is the ketone group. This is the alpha carbon. This has a hydrogen. This has a hydrogen. So we found these 2. This could potentially react with itself, or it could potentially react with this one. Now, let's look at this molecule. The alpha carbon is here, and since it's attached to a benzene ring, it doesn't have any hydrogens. It's already got 1, 2, 3, 4 bonds, because one of these is a single and one of these is a double. So it already has 4 bonds. There is no alpha hydrogen. So we have to lose one of these 2 groups hydrogens. This one is going to be less sterically hindered and more likely to be lost. So I want to redraw this with missing 2 hydrogens because we're looking at what happens after the dehydration. So I redraw this molecule like so. Now, which of these 2 is it going to attack? It could attack itself, okay, or it could attack this one. It's going to preferentially attack this one. Why? Steric hindrance. This carbon is much less sterically hindered than this carbon. So what happens is this becomes double bonded to this C, which continues to be bonded to an H and continues to be bonded to a ring like so. All right. So this is a major product. Why? This has no alpha carbon with hydrogen. Okay, sometimes I call them alpha hydrogens, which isn't technically correct. So no alpha carbon with a hydrogen. And this, why can't it attack itself? This is sterically hindered. So by having a sterically hindered ketone here and having one with no alpha carbons here that contain a hydrogen here, we are able to get a crossed aldol condensation followed by a dehydration. Now let's look at a different case. Let's look at a molecule, and I'm going to, since I made a mistake over here, I'm going to use a little bit more of the page this time. We're going to look at cyclohexanone, which we've seen lots of times. Now let's say we added to CH3, bond C, double bond O, bond C, bond H, bond H, bond C, double bond O, bond O, CH2, CH3. And again, we're going to add NaOCH2, CH3, followed by ethanol. Okay, so we add, again, a relatively weak base compared to LDA in ethanol. Now, remember that the first step of this reaction is to lose a proton from an alpha carbon. So this alpha carbon has 2 protons, the other one's the same, and this are possible for losing. Remember, back from the previous chapter, we lost these hydrogens preferentially because they're much more acidic, because there's 3 resonance forms, because there's electron withdrawing group, however you want to say it. These protons are much more acidic, somewhere around a pKa of 11 or something like that, 10 or 11. Here, these pKa's were like 18. So these are much less acidic. So we're going to lose this one preferentially. Then we have to, when we have this large difference in acidity, and we also have this, relatively bulky molecule, what we end up with is this losing the proton, but then after the dehydration, both protons. So we get CH3, C double bond O, bond C, double bond O, CH2, CH3. Okay, and it's going to attack this one. So we get double bonded to the ring. All right, and no, that's not a benzene ring, so it shouldn't have this in the middle. Of course, it can't be benzene and have a carbonyl group on it. So this is our major product. Water is the byproduct, and we get this in about 80% yield. Just for your curiosity, we get this in about 78% yield. It's about the same. Okay, so that is basically how this is working. So we can use 2 different things. One, we can use steric hindrance when there's a large difference in steric hindrance, and the fact that this one had no alpha carbon with a hydrogen on it to cause a mixed reaction to occur. We can also use the fact that there are large differences in acidity of the alpha, of the carbons attached to the alpha. Let me say that again. We can use large differences in acidity of the hydrogens attached to the alpha carbon. So in this case, these are very acidic compared to these. That causes this to lose them, and we end up with this type of conjugated product. In the next section, we'll look at intermolecular aldol reactions, where we have molecules that have multiple ketone or carbonyl functional groups, but they're not right next to each other. Because if they're right next to each other, what you can find is, you're going to end up with, you can't form rings because they're too close together. So we'll look at some intermolecular cases.